Welcome back to Physics with Miyoshi. Today we're here to talk about, or this time we're here to talk about simple harmonic motion, a little bit more about it. And if you recall from our discussion before, we talked about simple harmonic motion with a spring and how if it's on a surface here and going back and forth, you'd have an amplitude of A, a period of T. I probably forgot to mention that in simple harmonic motion we also have this thing called angular frequency, omega, and it's equal to 2 pi times the frequency, which in simple harmonic motion takes on this characteristic square root of k over m, where k is the spring constant of my spring here. And we're going to use that again later on in most simple harmonic motion. We can use an analogous type of equation for omega, or for our angular frequency. Also recall that with Hooke's law we have something called F is equal to minus kx, where k is the spring constant and the minus sign refers to the restoring force that the spring pushes on our weight with. So we'll remember those kind of things as we think about simple harmonic motion in terms of pendulums as well. In a pendulum we have in this case we have a little mass, a point mass, what we consider any kind of object with just a single point. We call that a point mass, and this mass has a mass of m. It's sitting along a string that's got a length of L, and I forgot to put those up there. So I'll just put those up there right now. L and M. And we look at this guy in a specific way to find its frequency as well, or its angular frequency. We have to look at torque, and you may or may not recall, torque is our perpendicular force times our distance. It's really a vector, but we just look at right now we're just looking at the magnitude of that torque. And the torque is the distance, or the force acted upon around a point of a certain distance from that point. So in this case, if I look at the length of my let's look at this over here now. If I look at the length of my pendulum and I think about the weight, the weight is the only thing applying any torque on it, because even though there's a tension on this mass from the string, the tension does not act perpendicular. Matter of fact, it can only act to that center point, so it will never give any torque. So the torque is applied only by this mg times sine theta. So the torque is my negative mg, because the negative sign again tells me it's restoring it, trying to go back to equilibrium. So we have mg sine theta and times our distance from the point the torque is acting around. So that's the L. So I have negative mg sine theta times L. Well, with a small angle theta, and as long as theta is in radians, with a small theta, then the sine of theta is approximately equal to theta. So this can be, our torque can actually become negative mg L times theta. And if you think about Hooke's law, it looks very similar to that. We can consider this negative mg L. We can consider that to be k prime, or something like k in Hooke's law. And this theta, again in radians, we can consider that to be kind of like our x in our Hooke's law equation. So with that kind of analogy, we can look at omega is, again, 2 pi f, which is equal to the square root of k, k prime here, divided by I, which is our rotational inertia, and that could be equal to our mg L, that's all under the square root sign, divided by ml squared. If we substitute in a point mass at a certain distance, that would be the rotational inertia, and we would look that up in tables and so forth. I wouldn't expect anybody to remember those kind of things. I would never remember those things either. But we were going to take those guys. We divide out the m's, divide out one of the l's by the other l, and we get omega for a pendulum is the square root of g over l. And the nice thing about this, the thing to remember, is that the frequency, the angular frequency, and the regular frequency of a pendulum is not dependent on the mass, as you can see. It's only dependent on gravity, which is on Earth is fairly constant, and the length of the pendulum itself. So, and again, if you had different configurations, maybe you have a length of something that's got a mass there, and instead of just a point mass, and a infinitely small or weightless string, then you would have different I values, and you might have a different equation here. But we could figure all that stuff out just by knowing my rotational inertia. So for springs, for simple harmonic motion, again we have our omega as square root of k over m for a spring, for the most part, and we have the same kind of analogy for the rotational, or for the angular frequency for a pendulum, square root of g over l, and more stuff with simple harmonic motion. There's lots more to it, but here's the beginnings and a little bit more explanation of some of the math and how we get to the pendulums. Remember, the important thing to remember about a pendulum again is that the angular frequency is not dependent on the mass. It's only dependent on the gravity and the acceleration due to gravity and the length of your pendulum. So, thanks for tuning in, and I hope to see you back again for more Physics with Miyoshi.